Hello, my name is Shafa Haridono, and today we'll be discussing Lab 2 of Physics 2212, Lines of Charge. Please excuse my voice, I'm like dying. So the purpose of this lab was to more accurately calculate the charge on the tapes we prepared from Lab 1, as well as the electric and gravitational forces acting on them by using the line charge model. Fundamental concepts covered include using Newton's second law and Coulomb's law to calculate the charge of the tapes when treating them as a single point charge like we did before, and then we will also have the law of superposition, which allows us to sum multiple point charges to get the net charge. This can then be applied through treating the tapes as uniformly charged rods made up of many point charges and using the following charge rod equation. A brief preview of the results shows that our new electric charge on the tape was about 2.31 times 10 to the negative 8th coulombs, and the electric and gravitational forces on the tapes, which should be the same in magnitude, turned out to be 1.97 times 10 to the negative 3rd and 1.96 times 10 to the negative 3rd newtons. To garner these results, we made the following assumptions. We no longer simplify the tapes to a single point charge, but instead treat them as uniformly charged rods that have equal and evenly distributed charges across their surfaces. In this experiment, we use the same positively charged U-tapes A and B created in Lab 1. We will let tape B be the system, and tape A as well as the Earth and its gravity be the surroundings. We assume both tapes are of equal charge. For the procedure, tape A is held stationary and tape B is held on top of it until they start to repel due to their alike charges. The distance between the tape due to the repulsion is recorded to later calculate the magnitude of their charges. Here's some images of my experiment. And the following measurements taken during the experiment can then be used to deduce the following. We calculate the force of gravity on the tape by using the tape mass. From here we recognize that because the tape is not moving, the force of gravity downward is equal to the electric force acting in the opposite direction. Using the distance between the tapes we measured as our vector r, we can utilize the equation for the electric field of a uniformly charged rod. We can see that the charge on the tape using this line charge model is 2.31 times 10 to the negative 8th coulombs. Below is the gross script code used to create a computational model of the experiment. For our constants, we are using the charge on the tape that we just calculated as well as the distance between them that we just measured. We then create a function for the electric field, our line charges, and also create the lines of spheres representing our tapes. Here I've chosen to create 20 arrows and spheres to represent the summation of forces. So as you can see, the electric force, which is shown by the white arrow, and the gravitational force, shown by the yellow arrow, are equal in magnitude but opposite in direction, since the net force on the tape should be 0 because it's not moving. So some discrepancies. Ideally, the magnitudes of these two forces should be exactly the same, but they are very slightly different. They have like a 0.01 difference between them, and this is due to probably experimental errors. I could have not precisely enough measured the distance between the tapes, but in the end I think it's pretty close. And for some questions, what if you had modeled each of your tapes as a single point charge? So like in the previous lab, when we treated these as point charges, the tapes had a charge of 1.33 times 10 to the negative 8th coulombs, but however now as a line charge model, they have a 2.31 times 10 to the negative 8th coulomb charge, and as you can see, the line charge is slightly greater. So why do these estimates differ? Which one is more accurate? Well, in this case, the line charge model would be much more accurate. This is because in real life, if you look at a piece of tape, it doesn't look like a single point charge in the center. It looks a lot more like an even, uniformly charged rod type structure. So that's why our second model is more accurate. And some parting remarks are that we can create even more accurate estimates of the charges on everyday objects by looking at them as uniformly charged rods, rings, spheres, whatever you want. This is why the law of superposition is so useful, because we can look at these shapes as a collection of many point charges and then take their summation to find their total charge. Thank you.